So I think we can give ourselves a minute or two, because sometimes what happens is I start and then people are coming in. It becomes a bit complicated to manage, both admitting them and reading. So maybe a minute, 11 or 2. Oh, it's 11 or 2, okay. Message. Yeah, all right. So let's get rolling. Thank you so much, everyone. It's great to see you guys. I'm sorry we had to cancel one of the talks, Phil Metzger's talk. Phil was very busy, and there was a real issue with connecting. He was traveling. So it just, we'll do it in January or February. That's the hope now. But it's so great to see everybody. Makes getting up on Saturday morning more than worth it. And we have a fantastic guest today. We have Andrea Liu, Hepburn Professor of Physics from UPenn, and she'll talk about how materials can learn to function. And Andrea's short bio, I wish I could add more, but unfortunately, I'll keep it short. Professor Andrea Liu is a theoretical, soft, and living matter physicist who received her AB and PhD degrees in physics at the University of California, Berkeley, and at Cornell University, respectively. She served on the faculty of the Department of Chemistry and Biochemistry at UCLA for 10 years before joining the Department of Physics and Astronomy at the University of Pennsylvania in 2004, where she is the Hepburn Professor of Physics. Liu is currently past Speaker of the Council of the American Physical Society and past Chair of the Physics Section of the American Association for the Advancement of Science. She's a Fellow of the APS, AAAS, and the American Academy of Arts and Sciences, and a member of the National Academy of Sciences. So with that, Andrea, it's over to you. Let us all mute ourselves. We will probably refrain from asking questions, excepting by raising a hand, just to keep things easier. So if you have a question, just raise a hand and I'll be tracking you guys. So for now, and then when she finishes, we'll keep it open. Thank you. Go ahead, Andrea.
Okay, thank you. Thanks so much, everybody, for coming. So yeah, I'd like to talk to you about some work that started actually a while ago, really initiated by my student Carl Goodrich with Sid Nagel, and that has led to things that I'm really very excited about now. So, but before I start, I just want to advertise the creation of a new center at Penn, Center for Soft and Living Matter. So this brings together, it's amazing, there are more than 60 faculty across Penn who self-identify as working in soft and living matter. And so the center is designed to bring us all together, and we're very excited about that. And so, please consider coming and joining us or visiting us. So I'm going to talk about how to design sort of biologically inspired functions into materials. And I'm going to start with a very simple one, which is to design the Poisson ratio. So the Poisson ratio, linear response, is directly related to the bulk modulus, B, and the shear modulus. Here, D is the dimensionality of space. Okay, so in 3 dimensions, it ranges from a maximum of 1/2 when the shear modulus is 0 and a minimum of -1. And values of the Poisson ratio that are negative correspond to auxetic behavior, where, if you stretch this way, it'll stretch in the opposite directions, in the other orthogonal directions. Usually, for example, you stretch a rubber band, it shrinks in the orthogonal directions. That's positive Poisson ratio. Negative Poisson ratio is the opposite. And an example of a system that does that is actually tendons have negative Poisson ratio. So the question is, can we tune a negative Poisson ratio into systems? Okay. And, you know, Sid Nagel and I got into this by thinking about, you know, the ratio of the shear to bulk modulus, which is what controls the Poisson ratio, is quite tunable in jam packings. But the Poisson ratio is always positive, okay? But it's still quite tunable. What do I mean by that? Well, if I talk about jam packings, these are particles which don't want to overlap, and if they overlap, you pay an energy cost for it. I can talk about it in a physics term, as I just did, where we have interactions, and if we're at zero temperature, we're interested in the minimum of the energy, so that at low enough density, you can avoid all overlaps and the energy is zero. Okay, but if you're at high enough density, there are unavoidable overlaps and you start paying an energy cost. Okay, but I can talk about it in a different language, which I'm gonna start talking about now, which is the way we start to think about things to be able to tune in anything, any kind of mechanical property we want. Okay, so what do we mean by that? So I'm going to use the language of constraint satisfaction theory, which is, you know, comes from computer science. So the idea is that we want to impose constraints on the system, and the constraints are that we don't want overlaps. Okay, so to impose these constraints, we introduce a cost function. So this is how people do machine learning. Okay, you impose a cost function, which is you penalize yourself if you violate the constraint. Okay, that's like introducing a repulsive interaction, and in our case, in the jam packings, the cost function is just the energy. Okay, and then the idea is that you can adjust degrees of freedom, which in this case are the particle positions, okay, in order to satisfy the constraints. And the point is that at a low enough density of particles, you can satisfy all the constraints and you reach the global energy minimum, but at a high enough density, you can't reach the global minimum and you end up in a local minimum, okay, which is a jam packing. So what do I mean by saying that the ratio of the shear to bulk modulus is tunable in jam packing? Well, this is what I mean. So that if you look at a jam packing, the ratio, think about this. So I'm going to now compress them to a high density. So there are lots of overlaps. Okay, and now I'm just going to release the pressure. Okay, just decrease the pressure. And when the pressure reaches zero, that's where the particles are now just touching, right? And what happens is that when you do that, okay, the ratio of shear modulus to bulk modulus drops continuously as a power law, going to zero at the jamming transition. And I want you to contrast that with the perfect crystal, the FCC, where if you do that, if you release the pressure, okay, the ratio remains absolutely constant, okay, until the point when they're just touching. And then beyond that, once they're no longer touching, it drops discontinuously to zero. So what you see here clearly is that the ratio of the shear to bulk modulus is a lot more tunable in the disordered case than in the ordered case. And this is what started us thinking. Okay, so now I'm going to switch gears to a different system, okay, which is derived from the jam packing. So now I imagine taking my jam packing, putting a node, okay, at the center of every particle, and putting a spring between every pair of overlapping particles. Okay, that gives me a spring network. And you see, the point is that in linear response, the mechanical response, the mechanical properties of this network are identical to that of the jam packing. Okay, and so when I imagine now lowering the pressure on the jam packing or lowering the density towards the unjamming, okay, that's like removing edges from this network, right? Springs just disappear when particles no longer overlap. Okay, so lowering the density is like pruning edges in this network. So now we can think about what happens when we prune edges in the network to try to understand the tunability a bit more. So the interesting thing is that suppose I just now take a bond of this network and I look at how much that changes the bulk modulus and the shear modulus, okay? So in a crystal, it's a series of delta functions, right? And how many delta functions you have here just depends on the complexity of your unit cell. If I add disorder, what you would expect is for this to fuzz out. That's not what happens, okay? What happens is that it doesn't just fuzz out into some Gaussian distribution around this, some value. It really fuzzes out completely so that there's a distribution extending all the way down to 0 as a power law, okay? Not only that, if I look at what is the correlation, if I take out a bond, how much does it change the bulk modulus versus how much does it change the shear modulus? Those two things are quantities are totally uncorrelated, okay? And if I look at the distributions of these, okay, I find that after some pruning, the bulk modulus distribution becomes identical to the shear modulus distribution. And we actually, I'm not going to go into this, but we have some understanding of why it has this functional form. Okay, so this raises now a really interesting possibility. Now that we know that if I take out a bond, how much changes the bulk modulus is uncorrelated with how much changes shear modulus. Now I can start playing some games, okay? So I can imagine taking this thing and introducing what I'm going to call edge demons. In this case, a pruning edge demon, just a pair of pruning edge demon, just a pair of scissors that can cut any bond I want, okay? Now, if I prune randomly, there's a very interesting result from the lighting group showing that the ratio of the shear to bulk modulus doesn't change at all as I prune, okay? It's just constant, okay? But now, suppose instead of doing that, I prune the edge that changes the bulk modulus the most, okay? So that's a greedy edge demon. If I do that, right, then each time I'm decreasing the bulk modulus by the maximum amount I can, but what's happening to the shear modulus? Well, it's as if I removed it at random, okay? So it's picking something, it's like picking from the mean of the distribution, not from the top edge. And so what happens is that the ratio of the shear to bulk modulus, because I'm decreasing the bulk modulus more than the shear modulus, this goes up as I prune. And it goes up by many orders of magnitude. It's incredibly effective in changing the ratio, okay? And let me just remind you that the Poisson ratio, when it crosses 0, that corresponds to where the ratio of shear to bulk modulus is dimensionality over 2. So 3/2 and 3 dimensions. That's what you get for cork, for example, which is why it's so useful for stopping wine bottles. But anyway, we see that we quickly get above this value. And as I shoot above that, the Poisson ratio is getting more and more negative, okay? So that in the limit where this goes to infinity, the Poisson ratio approaches its most negative possible value, okay? So, so we can do it, okay? Another way to do it is by actually pruning the bond that changes the shear modulus the least. And that's interesting because you see what you're doing there is now you're choosing something from the bottom of the shear modulus distribution, which, as you remember, goes all the way down to 0. So that doesn't change the shear modulus at all. Whereas what you're doing to the bulk modulus is it's as if you're pruning things at random. So it's like taking away from the mean of the distribution. And so again, the ratio of the shear modulus, the bulk modulus increases and eventually goes past 3/2. Okay, and you can get other things depending on how you choose to prune, right? If you choose to prune bonds that change the shear modulus the most, then the ratio goes to 0 very rapidly, for example. So this is very interesting because what this says is that I'm pruning the bond that changes the bulk modulus the most. And that's equivalent to doing gradient descent on the bulk modulus, okay? If I think about doing gradient descent with degrees of freedom, what are my degrees of freedom? They are what we call learning degrees of freedom, which in this case is just the presence or absence of a bond. I'm allowing the bond to be there or not be there, right? But I can imagine a lot of other learning degrees of freedom. I could change where I want my edges to be. In other words, I could cut one here and I could put it somewhere else. Okay, I could tune the stiffnesses of the edges, the spring constant, or I could tune the equilibrium lengths of the springs. All of these work. Okay, with all of these, we can do this. and we can do gradient descent on the bulk modulus, okay, and we can tune it to 0 or to some other value if we please, okay. And it turns out that any mechanical property that can be written as the sum of the properties of edges, okay, can be tuned in this way. All you have to do is construct the appropriate cost function and then minimize it, okay? So this lets us think, okay, what else can we do? So, so there's this another biologically inspired function, which is called allosterium in proteins. So, and this is used by, for example, many enzymes to turn them on or off. So the idea is that here's a substrate molecule. It wants to bind to this enzyme and get chemically modified, you know, phosphorylated or something, okay? But right now it can't bind, okay? It cannot bind until some other molecule called the regulatory molecule binds over here. Once that happens, there's a conformational change in the protein, which now allows the substrate molecule to bind, and that turns the enzyme on. So the idea is this regulatory molecule turns the enzyme off. And there are also many cases of regulatory, turns it on. There are also many cases of regulatory molecules turn enzymes off so that they can control whether they're on or off that way. Okay. If we think about this in physical terms, what are we doing? Well, when this regulatory molecule binds, it's exerting a strain, okay, at this source site. And what it's doing is it's causing a conformational change of the protein to cause a strain over here, which is of the same order of magnitude as the strain over here, which then can control whether this thing will bind or not, that can open this up so that this can bind, okay? So this is actually a very common function in proteins. And so what we're seeing is a localized strain at the target due to a localized strain applied at the source, okay? And now you say, well, what's the big deal? Elasticity is long range, okay? Why can't you do that? Well, the point is that the deformation actually decays quite rapidly with distance. And on the scale of a typical protein, what you would expect is the response here to be 2 to 3 orders of magnitude lower than the strain that you applied here, okay? So to get a strain here, which is the same order of magnitude, a response of order 1 to this strain at the source is really unusual. Okay, so we were talking about this, and my wonderful colleague Eleni Katahori said, "Oh, you know, brains do the same thing." It's like, really? So it turns out that brains are really hungry for oxygen, right? That when you're doing something like right now, I'm talking, I need a lot of oxygen going to my speech cortex. And what the brain is doing is in real time, it's adjusting. So that what it's doing is it's taking the vascular network in the brain, the system of blood vessels, okay, which has blood coming in through the arteries, okay, and it's directing extra blood flow right now to my speech cortex, okay, and it's doing that by dilating and contracting individual blood vessels in this network, okay, so that's the same thing. I've got a source and I've got a target, right? In this case, the source is the input arteries into this vascular network, and the target is my speech cortex. But the system can adjust, right? If I start walking instead, right, it'll have to go to, it'll send blood flow to a different part of my brain. And ideally, I'm thinking as well. So, so the interesting thing, the really nice thing, right, is that the spring network, a network of central force springs, which I'm writing down here, the energy, okay, is mathematically very, very similar to a network of pipes, okay, in a flow network, okay? And in particular, flow networks are just really one-dimensional versions of mechanical networks. And both of them are just, you know, governed by, they have this conservation rule. And the easy way to see that is that, right, in a mechanical network, I need to have force balance on every node to be in an equilibrium. And in the flow network, right, I have Kirchhoff's law, I have to have no net current at each node. Okay, So, and that's the same thing. It's a very similar mathematics then. Okay, so so now what are we going to do? What we're going to do is we're going to tune in allostery either into central force spring networks or into flow networks, into both of them. Okay. Now, one way to do that is to take proteins which actually exhibit allostery, and there's a wonderful community of people who take these folded proteins and turn them into spring networks. Okay, we're not going to do that. Okay, what we're going to do instead is we're going to start with ensembles of networks that in our case we got from jam packings because that's what we had around. Okay, and then we're going to tune in the allosteric function into each network. Okay, and we're going to do that in the same way that we're going to construct a cost function, which says if my target strain, I'm going to call my source strain 1. I'm going to choose units where it's 1. If my target strain, I want it to be delta. If it's less than delta, I'm going to pay a price. Okay, so I want the target strain to be at least delta. And how am I going to do that? I'm going to have learning degrees of freedom, which are the bond stiffnesses or the presence of absence of bonds. Okay, and I'm going to tune it that way. Or if it's a flow network, right, my learning degrees of freedom could be the conductances of the edges. All right. So that's what we're going to do. And this is just to show you that it works. So here I have a spring network. Here's my source. And now I'm doing it with, I happen to be doing this in this case with periodic boundary conditions. Okay. So here's my source strain. Okay. Which I'm calling 1. And here's the strain at the target. That's read out in this window here. And it starts out before I do any tuning. It's, 0.005 compared to the source, which is 1. Now I'm going to start tuning the spring constants, okay? Going downhill in my cost function, okay? The blue dashed ones are the ones that end up getting removed entirely or reaching some minimum value. And as I do that, what you see is the strain at the target event goes up and it finally reaches the desired value, which is the same as the source, okay? Here it is for the flow network. Here's the pressure drop. I put in a pressure drop of 1 at the source. Here's the pressure drop at the target. Now I'm tuning the conductances of the edges until I get the desired pressure drop, which in this case is 0.2. It goes up and up and up until I reach 0.2. Okay, so I was able to do this successfully. So this works. And the amazing thing, it actually works well more than 99% of the time. Almost all the time you can do it. Okay. We can do it highly successfully with very little tuning. Okay. So it works. It's great. Okay. But not as great as we would like. Why? Because this is not scalable. In order to do this, I needed to know all the spring constants of every single spring in my network or all the conductances. I had to know the exact structure of the network, right? And I had to be able to go in with my little edge daemon and change the spring constants or conductances as I wanted to, okay? That's possible on the computer, no problem. But if we want to do it in real life, on a real material, that's a problem. We can't do that. And that's the thing, that designing by minimizing your cost function, which is how you do computational neural networks. You're minimizing a cost function every time you train a neural network, right? It's an inherently global procedure. And we have to know the cost function, which depends on all of the microscopic details of the network. And then we have to be able to minimize it. So you have to do the computation to figure out, oh, what do I have to do in order to minimize this? Okay, then you have to go in there and do the right manipulation to minimize it. Okay, so that's not very good in real life. So here's the question: can materials learn how to function without edge daemons and without this computational step? Okay, so this, in fact, so it was this wonderful postdoc that Sid and I had, Daniel Hexner, who figured out that the thing to do was to remove bonds that change the bulk modulus the most or change the shear modulus the most. But in fact, that's not what we initially did, okay? In our first attempt on this, what Carl Goodrich did, was to say, let's just prune the bonds that contribute the most to the bulk or shear modulus, which in fact means let's remove the bonds that are under the greatest stress. Okay, in the case of the bulk modulus, the bonds that are under the greatest stress, if I apply a compressional strain or an extensional isotropic strain, the ones that are under the greatest stress are the ones that contribute the most to the bulk modulus. Okay, so that's what we were initially doing. So we went back to that and started thinking about that. It's like, wait a minute, okay, what's the system doing? Well, if I put the system under, let's imagine just taking my network and swelling it, dilating it isotropically. Well, the system's going to automatically adjust all the node positions in order to minimize the elastic energy. Okay, and now if I say, oh, well, let's have special bonds, okay, which people can actually make in polymer networks that break above some threshold stress. Okay, then if I under my applied isotropic stress, the ones that are going to break are the ones that are under the most stress. They're going to break first, right? And those are the ones that are going to change the bulk modulus the most. So the system is going to automatically tune itself to be auxenic. Similarly, if I took that same network and I applied a shear strain, the ones that would be under the most stress are the ones that would change the shear modulus the most. And that would then drive the ratio down and it would drive the Poisson ratio up. Okay? So this is actually, when we think about it, bond breaking under stress is an aging process. It's a non-equilibrium process, right? And the difference between a disordered system and a perfectly ordered one is that in the perfectly ordered one, right, all the bonds would have the same reaction to isotropic swelling. They would all break at once. But in the disordered system, right, it's going to age, it's going to break bonds along some trajectory that depends on the stress that I apply to the system. So that it drives it in the direction I want. So what it says is that by changing the boundary conditions on my system, okay, I can prune the bonds that are under the greatest stress. And that's similar to pruning, that has a similar result, it turns out, to pruning the bonds that change the bulk modulus the most. But pruning the bonds that change the bulk modulus the most, remember, I was telling you, that's gradient descent on the bulk modulus, which I can take as my cost function. But the system, right, is minimizing only the elastic energy. That's what it's doing. And so what that tells us is that the cost function is similar to the elastic energy when I apply the proper strain or the proper boundary condition. Okay, so that mysterious cost function is actually pretty similar to the elastic energy. And the cool thing about that is if that works, then what it's saying is each bond just responds to the stress on it. It doesn't need to know what another bond over there is doing in the system. It's just responding to what it itself feels. And that's a local rule. It didn't require any computation, it didn't require a computer to say, okay, you bond there, change your stiffness. Okay. And this actually works. So Nidhi Pashin, the student, laser cut these systems from a jam packing. Okay. I'm going to focus on this one because it's the most similar. So it's cut from the network where I put a node at the center of every particle and then an edge between every pair of overlapping particles. Okay, so she laser cut this out of solid foam. Okay, then she compressed it, put it under a uniform isotropic compression and weighted. Okay, and the idea is then, right, this is we're directing the aging process so that regions that are under higher stress are going to deform plastically under this strain, okay, than regions that are under lower stress. Okay, so she let it age, then she took it out, and what does it do? Here's the Poisson ratio as a function of the strain at which it was trained. So the training was to compress it and hold it there and wait. Okay, that's the training process. This is the strain at which, this is how much we compressed it. Okay, or she compressed it. And what you see is that the jam network, these blue ones, okay, the Poisson ratio drops as you increase the amplitude of that training strain, and it does actually go negative. So this works. We were able to tune it to become auxetic. Okay, we didn't even know in this case what the learning degrees of freedom were. We didn't need to. This is a complicated system, right? If you try to do it on the computer with finite element or something, okay? But we didn't even need to know what they were, and the system adjusted itself, okay? So then it's like, that's great. How about Allosterium? Or actually, before I do that, I'm talking about something that's, sorry. We can actually do this while driving the system in another way. So, so now what we're going to do is this is on the computer, but we're going to use the equilibrium spring lengths and a central force spring network as our learning degrees of freedom. And now we're going to try to make this network actually auxetic again. Okay, so we're going to apply a source strain where we squeeze it like this. Okay, now what we want when we squeeze it like this, we want the orthogonal direction to come down. Okay, so we're going to apply not only the source, this, but we're going to apply the target response that we want, which is to squeeze like this. And that corresponds to squeezing the whole thing isotropically. Okay, and now we're going to use this rule for the equilibrium lengths. And this rule is nothing less than we're going to minimize the elastic energy with what this boundary condition where we apply the source and the target that we want. So I'm going to call that the clamped condition. Okay, we're going to do gradient descent on that with our degrees of freedom, which are the equilibrium lengths of springs. Okay, and let's do this in an oscillatory fashion. So expand, compress, expand, compress. Okay, isotropically. What happens? So what this is saying is, right, we're using the elastic energy itself. We are explicitly now using the elastic energy itself as the cost function with the right boundary conditions, the desired boundary conditions, and we're going to minimize this with respect to the learning degrees of freedom. And this works. Okay, so that after many, many repetitions of the oscillations of driving, okay, the system reaches a negative Poisson ratio, okay? And interestingly, it reaches it over the range of the training strain. Okay, so, all right, so we have this, we actually do reach this Poisson ratio very close to -1. All right, and we can do this with Allosterium as well. Okay, so for Allosterium, we're going to apply a source strain here at this green bond, okay? And then we want the target strain at this red bond. So how we're going to do it, same thing. We're going to apply this clamp condition so that not only do we oscillate the source bond, okay, but we oscillate the target bond the way we want it to respond. Okay, we apply the desired strain to the target, and then we let the system go and minimize the elastic energy with that boundary condition. And this shows the readout oscillation. So the green is the source that I'm applying. It's going between 1 and -1. And the red, right, is the target. And you see that as time goes on, as it ages along, this target response goes up and up and up, and eventually it approaches the source strain. So we have successfully tuned in Allosterium into this network. Okay, so this was great, very excited about this. This is beautiful work of Daniel Hexner's. But it turns out that it doesn't always work. Okay, so directed aging actually requires some coupling between the source and target. You don't want them to each do their own thing when you drive it. Okay, and it turns out that this works when the system is near the limit of mechanical rigidity. In fact, where it's near, if you start with networks derived from jam packings that are near the jamming transition, it works very well. But if you're well above the jamming transition, so you have a lot more edges per node, then it actually does not work. You can get around that, but it actually, this totally fails for flow networks. Okay, so this is where now my postdoc Naki Stern comes in, came up with this really great way of tuning things, borrowing from what's been done in machine learning and neuroscience. So based on the ideas called contrastive Hebbian learning and equilibrium propagation. Okay, so the idea is what we want, right, is to apply the source, not to do anything at the target, the free case. And we want the target to have the response that we desire. Okay, that's what we want. But what we're doing, right, is we're applying the source and we're applying the target. Okay. What we want, actually, we want the free to be the same as the clamped. We want the free to produce the same result as in the clamped case. So this means that what we want to do is we want to minimize the difference of the elastic energies between the free and the clamped case. We want these to be the same. So instead of minimizing the clamped case, okay, with respect to my learning degrees of freedom, what I really want is to minimize the difference between the free and the clamped case, because I want the free to be the same as the clamped. Okay, so in the case of flow networks, then what we're going to do is we're going to adjust the conductance of each edge, okay, to go downhill in gradient, depending on the power dissipated in the clamp case minus the power dissipated in the free case. Okay, that's the difference that we want to minimize. Okay, and then there's another nice trick that came from equilibrium propagation, which is that you want to not just put in the clamp case, don't just get greedy and say, oh, I want to get the target response that I want. You just gradually nudge it towards what you want. Okay, it turns out that that's more effective. It's sort of like the oscillatory driving. Instead of just applying what you want, we do the oscillatory driving everywhere in between, and nudging it is very similar to that. And that works. So if I look at the cost function in a flow network, or this is the error, this is the difference between what I get and what I want. Okay, what you see is that goes to 0. You can train it in this way. Okay, so this actually does work. And it's very, very similar to doing gradient descent on that error. So the rule that we have is saying we want the free to be the same as the clamped. Okay, it's very similar to doing gradient descent on the error. The response in the free case is the same as this response that we want. Okay, and directed aging, just to say, corresponds to dropping this term. Instead of looking at the difference, you're just minimizing the clamp case. Okay. So this is great, and it actually does work. Okay, can we implement it in real life, in a real system? Turns out to be really difficult, because what you need to do is to compare what happens in the system with 2 different boundary conditions, and it can't have 2 different boundary conditions at the same time. Okay. Right, you want to do gradient descent on the difference between what the power dissipated in the case of a flow network, or the elastic energy in the case of a central force or a mechanical network, but under 2 different kinds of boundary conditions. So how can you do that? So this is where our very clever experimental collaborators come in. This is Sam Dillavu working with Doug Durian. And they came up with this very clever idea of not trying to use 2 different boundary conditions on the same network at once, which is really difficult, okay, but which is impossible, okay, but to have 2 different networks that are coupled together. So each network, each edge of this network is actually, I have 2 identical copies of the network. And one network I apply the free condition, the other network I apply the clamp boundary condition, And then there's clever circuitry, in this case, to compare what happens. Because remember, an electrical network of resistors is mathematically identical to a flow network, like in the brain. Okay, it's mathematically it's the same problem. So what they did was they decided, okay, let's implement this in an electrical circuit. So I just had, they put in variable resistors on each edge and had the circuitry to compare what happens with the two boundary conditions. And here's a very simple 16 edge network. Okay, well, it's amazing. It really works. Okay, this really works in real life. Okay, so this is a case of classification. So this is now saying, can this network do something that's much more sophisticated than Allosterium or the kinds of things we were trying before? Can it actually do classification? So this is a famous early data set, the iris data set, where there are 3 different families of irises and 4 measurements, the size of these sepals and the size of the petals. And from these 4 measurements, okay, the idea is to classify irises correctly into these 3 families, okay, with some training, given some training examples. Okay, so in this case, they take 4 nodes, okay, these are the red ones, plus 1 that's at ground. So 4 nodes, which give you source voltages, which correspond to these 4 measurements. Okay, and then there are 3 target nodes, which were chosen for the different families. Okay, this family, that family, or that family. Okay, they're trained on these examples, and it works. As you look at the classification error, as you do these training steps, you let the system adjust the conductances of the edges. Okay, according to the couple learning rule, or actually a crude approximation to the learning rule, the error goes down, okay, and eventually you can classify it with an accuracy of 97%. Okay, it really does work, even this tiny little system, this prototype. And this is just to show this learning circuit learning as we go. So first, for example, we tune it to do that iris classification. Then take the network that's in that state, the resistances are tuned to do the iris data set, and say, no, 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 I don't want you to tune irises, I want you to do Allosterium. Okay, in other words, I have 1 node at ground, and I want to tune another node. This is my source node, here's my source voltage, and I want to tune the target voltage to have some value. Okay, yeah, it can do that. Here's the error, starts out large, it gets small. Okay, they say, no, I want to have now 1 source and 2 targets. No problem, it learns that. Well, how about 2 sources and 3 targets? Okay, does that. Well, how about 1 source and 4 targets? Yeah, it can do that too. Then what Sam did was he trained this to have to solve a linear regression problem. Can you solve 2 equations and 2 unknowns? Solve for the 2 unknowns. Okay, here's 1 set of equations, it did it. Here's the second set, yeah, it did it. And say, okay, now go back and do the first thing, this Allosterium. Again, it did it. But the interesting thing is that the state of the resistors in this case was different from the state here. Okay, it found a different solution that also worked. Okay, so the fact that there were many different, there was more than 1 possible solution to the problem, okay, suggests that actually we have more learning degrees of freedom than we really need to solve these problems, even with 16 edges and tuning the resistance of each edge. That's only 16 variables that I'm tuning. That's actually enough to do all of these things, more than enough. Okay, so what happens if we start damaging it? And that's interesting because, right, brains are actually incredibly, real neuron networks are incredibly robust to damage. You can remove half the brain and a person can still function. Okay, you know, computers are not robust to that kind of damage. Here's just a tongue-in-cheek example of an iPhone. You saw it in half and it stops working. Okay, so, but there's no central processor in these networks. Each edge is learning on its own. Okay, So now we can think about doing damage. I'm just going to start cutting these edges, just removing them. And as you cut them, you find that, yeah, in each case, it can just keep learning. Okay, we can remove, in this case, 5 edges out of the 16, and it can still learn what it wants to learn. Okay, it's robust to an incredible amount of damage. So, so we're just incredibly excited about this, right? So just to say, what we're saying is that disorder networks are incredibly adaptable, okay? And you can basically tune in just a huge number of different mechanical properties in a mechanical network, or flow properties in a flow network, okay, by using a cost function and optimizing it, okay? And all you need is to have enough learning degrees of freedom, many more learning degrees of freedom than you have constraints, and then you can do it, okay? And this provides a systematic way of designing any response that can be written as a sum of properties of edges, okay? But the nice thing about coupled learning is now we have a systematic way of developing local rules to train any desired response, not to do it by minimizing a cost function, which requires a computer, okay? But we have local rules. And if you can implement those local rules, that is an if, but we manage in the electrical network, okay, if you can implement those local rules, then you can have a system that learns on its own, okay? It doesn't need a central processor. It doesn't have that bottleneck. It's incredibly robust. So it combines the simplicity of an artificial neural network, okay, that allows it maybe so that we can do theory and understand what it's learning, okay, with the robustness and flexibility and the the distributed learning of a real neuron network in the brain, okay, which is of course much harder to understand. So I think I'll just stop there, and I'll thank the people who actually did the work here, and my wonderful collaborators, Eleni and Sid and Doug, for their help on this work. Thanks a lot.
Fantastic. Thank you so much, Andrea. This is great. We're open for questions, so you can unmute yourself and ask questions. Joshua, go ahead.
Very nice talk. In the protein systems, your allosterium tuning. I was just wondering, how does your tuning approaches take into consideration the well-known biochemical activity and interactions of proteins? And then my other second question, you talk a lot about bonds. It wasn't clear to me, are you referring to physical, chemical, or physical-chemical bonds?
So in the case of proteins, and this is the direction that I would like to go, but we have not gone in this direction yet to tune actual proteins. Okay, so there, as I say, there is this community of people that take folded proteins and then convert them into spring networks, and they have actual covalent bonds as well as, hydrogen bonding and van der Waals interactions and electrostatic interactions that go into how they turn these things into networks. Okay, so one can imagine doing something through that. This is not a direction that we have gone. What I would rather do is to go in there and actually then swap in and out amino acids, okay, whole amino acids, and see, can you tune the protein to have this by introducing a cost function which says I want this response over here. Okay, this is not something that we've done. It's very, very hard, because when you start swapping amino acids in and out, it may no longer fold into the same structure that you had before, and that screws everything up. So you actually also have to check the folding, and this has just been beyond our capabilities to do. but I'd be very interested in pursuing that with a collaborator.
Thank you
So,
very much.
yeah. Great question.
Oh, go ahead, Subbu.
Hi, thank you very much for the talk. Enjoyed it. I have two questions, if I could. The first one is, would you have any comment on what might happen if you consider nonlinear springs, say, and harmonic springs? And secondly, would synchronization of an oscillation in that network, do you think that would have any effect on this learning?
Okay, so the first question, shoot, remind me of the first question.
Sorry, yeah, nonlinear springs.
The nonlinear springs, absolutely.
Yeah.
So that will just make it more powerful to learn. So there's been a lot of work in machine learning, right, or in neural networks that shows that, you know, if you have nonlinear networks, the capability of learning goes way up. Okay, it's much easier to learn. So, we think that should just make it more powerful. And so the second question was, remind me of that again. Sorry, more than one at a time because I'm thinking about it.
Synchronization.
Okay.
Yeah.
So what do you mean by that? Just make sure I understand exactly what you mean.
Right. So if we drive let's say we drive a network of springs to synchronize their response, do you think that would have any particular effect on this learning process that you're trying to accomplish here, that you talked about?
So the question is, does each spring have to update at the same time?
Yeah, or would we derive any benefit if each spring were to update at the same time?
Yeah, so that's a great question. And we've actually looked at this in the 16 edge networks in the learning circuits. Okay, because initially there was a clock so that each resistor would update at the same time. Okay. Now this is the work of an undergraduate, Jacob Wyckoff, who's been working with Sam Dillaboo and Doug, to turn that off. And it actually can learn better if you don't synchronize everything. So if you just allow things to do it on their own time, you can actually end up even getting better training. So
yeah, thank you.
It's sort of like stochastic gradient descent, it turns out, in machine learning. The reason why that works better.
Yeah, thanks.
Further questions?
I have a question, Surajit.
Yeah, go ahead, Kevin.
So, Andrea, a long time ago, I was studying osteoporotic bones. And what happens in the porous bone network is it's a random network, but the difference is that the highly stressed links become stronger. What would that do to the systems?
Yes, so that's exactly this kind of directed aging. And in fact, Sid talked to you.
Yeah.
We came back very excited about this. And we started thinking about it. And I actually looked in the literature, and the rules for this are a lot like the rules for updating neural networks.
Okay.
So in fact, the bone is learning, right? Mm-hmm. By repeatedly stressing your bones, the bone is learning to get stronger.
Right.
It's a very, very similar process. And this is not the only biological system that does this, So if you think about this, for example, the cytoskeletal network, actin, there are all these actin binding proteins, okay? For example, there's cofilin that tends to break bonds that are are they above or below? I forgot. I think below some threshold stress. So by putting the system under the stress state, the system is actually got these things that are adjusting the topology of the network.
Right.
Okay. in response to those stresses. So it is doing directed aging. And they're cross-linking proteins. And if the cross-link is under too much stress, they'll just pop off.
Okay.
Okay, so it's got to be that the cytoskeleton is changing its mechanical properties under stresses.
Yeah.
So John Crocker and I now have a postdoc, Marco Galvani Cunha, who's looking at this, so trying to find a simple model to test this. And collagen, there's collagenase, which clips collagen fibers that are under low tension. And it's always been thought, oh, it's use it or lose it, you know? It's nature being thrifty.
Yeah, yeah.
If this collagen fibril isn't being used, let's use it somewhere else. Well, but just by clipping it, you are actually changing the mechanical response.
Right, right.
So maybe it's losing it to use it too.
Yeah, actually, the other nice thing about that is this came from a discussion with Sid, that the strength of the bond can be measured by looking at the ratio of low frequency to high frequency linear response.
I see, you can actually measure in the bone.
Yeah, in the bone, yeah.
Oh, that's fantastic. So you can actually measure it changing in real time.
We have shown this in model systems. I've tried to get somebody to do the experiments, but it's tough to get.
Yeah, that's the frustrating thing, right?
Yeah.
Is getting somebody to actually do the experiments.
Right.
Oh, okay. Okay. Well, this is great. Let me look at your papers.
Okay.
I think
I can send some to you.
Yes. Okay. Great. Thank you.
I had a comment on actually Gemunu's question. So it appears that the system has some remnant memory, right? So it's a memory base that is being tapped into for strengthening that weak bond into a stronger one. So all one has to do, well, all one has to do is to basically build into the way we are thinking or modeling the memory part of it. And
exactly.
And I had a related comment that when he talked about the two boundary conditions and the way Doug was approaching the problem with two copies, the copies don't even have to be perfect copies, I don't think. You can actually, there may be advantages of having dissimilar copies as opposed to similar copies. You might actually be able to build in more learning into that dynamically as you do the system. So actually, Doug can try it out. This should be something one can check.
Okay, that's interesting. So you're saying if they're topologically different?
Yeah, slightly, not terribly, but slightly. They're sort of similar, but not the same. Because it might give you learning / info about the similar states that can take you to the point you want, which you may not have foreseen. You may have an over-constrained system. It may not be needed.
Okay, that's really interesting. All right, yeah. Okay.
If you find something interesting, drop me an email, because I'm quite intrigued by this whole thing, because this morning, for a completely different reason, I was thinking about the whole idea of, adaptable Hamiltonians, which I never really looked into anyway. But then I was thinking that this should be possible to do, at least for simple cases, and one can actually figure out how any system learns. So actually, I didn't know what you were going to talk about, but somehow I think there was a student I was arguing with in class recently. He had a good question, and that led to this thinking. And that experiment and this whole bone business is fascinating. So thanks a lot. There is a question here from Hema. Hema, go ahead.
Hi, it's a nice talk. Thanks for that. Can you hear me?
Yes.
Yeah. Okay. From what you talked, I get reminded of Nassim Taleb's Antifragile. That's just a comment. Antifragile is something that when you stress, it improves its performance. There's a book by book called Antifragile by Nassim Nicholas Taleb.
Antifragile. Okay, that's a good term. So
Antifragile.
that's like Yamanu's bones. Yeah.
Yeah,
Okay.
and there is some other connection that I also thought about. It's called compliant materials. In engineering, there's a term called compliant material where you apply stress at some place and you expect this is a material that is a same material. You cut it out, and when you press it someplace, if you design it properly in a geometrical, if you specify its geometry properly, you can get the stress at any place else, like a fork or something like that. So basically, with the same material, just by dictating the geometry of the object, you can transfer stresses to wherever you want. So that's like Allosterium. It's Allosterium, exactly.
Yeah.
So my question, the first question is that because disordered materials are disordered, you can store a lot of information in them. It's not like crystals, because all the positions are equally occupied. So it's basically there is no memory. There is no space for storing any information there. Whereas disordered materials, the number of bonds you can vary, the position that you can vary. So there's a lot of variation there. So you can store a lot of information. In that respect, you can teach pretty much anything to them.
That's
you
right.
Can store any amount of information. So that's an observation. The second question is related to systems biology. Instead of looking at the network in a spatial dimension, you can look at it in a temporal dimension where you have reaction network, and these networks are reaction networks. So one molecule catalyzes or inhibits another molecule, and that in turn catalyzes some other molecule. So you have a network in a spatial temporal network. And when on the surface of the cell, when you have some like a glucose molecule or something that comes and sits on a receptor on the surface of the cell, the information gets transferred, and something happens at the DNA level. So can your model, basically it's this Allosterium, but applied to a spatiotemporal type instead of just spatial type?
Yes.
So in that respect, can you use the same model to understand specificity in biological systems, like a particular immune molecule, let's say immune stimulant, comes to the receptor, sits on the receptor, and it creates a specific impact at the level of DNA. So that's Allosterium at a more rather general level. Can your network be used for modeling those kind of scenario? And can it be used as a tool for systems biology to study such specificity effects in systems biology?
Yes, we suspect so. So we haven't done it. This is a direction that I'm extremely interested in going. Another kind of system is ecological networks. You introduce wolves into Yellowstone and the beaver population goes up. That's Allosterium, right? And so
on the river course changes.
Yes, and river course changes as well. So yes, we do think that these ideas can be extended to those kinds of problems as well, and we haven't done it yet, but it is definitely on our radar screen. In fact, I think of one of my slides. Yes, how general is this? Biochemical signaling networks, ecological networks, et cetera. We would like to know if we can tune all of these things with these ideas. Yeah, it's extremely exciting.
Thank you.
Let's go to Ridwan, and then Joshua has a second question. But Ridwan, go ahead.
Yeah, thank you. It's very, very interesting talk, Andrea. I do want to take a little bit issue, but making crystal being not so interesting, because I would argue to you that obviously once you introduce defects, it does become actually a disordered network in that sense. So I'm going to just comment about two possibilities. For example, if I have a highly polarized system and I look at conformation of absorption on the surface, for example, if I introduce defects into this polarized system, I can change the conformation of particular absorption of molecules on the surface simply by essentially charge transfer effect. But it does actually, in fact, nowadays, fourth generation of high dimension neural network system that is being developed for interatomic potential does try to incorporate obviously the charge transfer, so by which you can actually tune in, for example, conformation on the surface. So that's more of a I would argue it's a network sort of interaction that would tune in things that are far away from the original source of where defects bury underneath the surface. The second part would be something like, for example, lithium diffusion, right? We have a lot of corporation motions in the battery system, for example, where again, there could be some adjustment being made far away from the system. And then you can tune in basically, let's say the mobility of through the channel or intercalated system. So I think even with the crystal system, you can actually, I would say, depending on basically what the species that you are identifying as, to be in that disorder in the manner that where long distance sort of control can be made. That's all I got to say. Thank you.
You're absolutely right. And in a way, the perfect crystal is a straw man, because as soon as you introduce any imperfection into the crystal, very, very rapidly it behaves just like the disordered case. In fact, it very, very rapidly approaches the fully disordered case. And so if you started with the crystal, just introduce one defect or just chose to break one bond, for example, in the tuning by pruning sort of thing, very rapidly it would approach the same distribution for the changes of the bulk and shear modulus that I showed you for the fully disordered system. So it requires almost no disorder at all to approach the fully disordered limit. And so yes, you're absolutely right about that.
Let me just add, in fact, actually we can do sort of the reverse, which is basically you may even, talking about the surface conformation, for example, you may be able to control or sort of engineer surface conformation or configurations by tuning in basically what's underneath. If we can actually train this process basically by defect concentration or the way they distribute it.
That's right. Yeah, it's really just, we're all sort of a bit brainwashed from taking condensed matter physics or teaching condensed matter physics and spending a whole semester on the perfect crystal, and it gets us so far, right? But here are effects that the perfect crystal just doesn't have.
Yeah. Joshua, you want to go ahead?
Yes, so in the oscillatory experiments you talked about briefly,
Yeah.
I'm assuming that the source and target stresses are selected to be in phase with each other. So I'm just curious, can your modeling be extended to systems where the oscillatory application of the stresses are out of phase, for example, for viscoelastic systems?
That is a great question. So yes, we can train it out of phase. All we have to do is apply a target strain, which is out of phase with the, in our clamped condition, the target response is out of phase with the source, and then you get it. Yeah, you can do it in phase or out of phase. Now, remember, there's no dissipation here. It's just a fully elastic system, and we're just training it this way. But what this says is exactly, what you're saying. If I now put on a compressive strain on my source bond, the target strain will open up. Or if I do like this on my source, then the target will
Right.
do.
Right.
Yeah, great question. Yes.
Right. Thanks.
You're absolutely right.
Yeah.
Further questions?
I have a question.
Yeah, go ahead.
When I hear the title as Allosterium, I'm thinking of the hemoglobin. Okay, because it's very important in biology to have a very good oxygen absorption. And okay, so have you looked at specifically using your learning network to study the hemoglobin and see whether the hemoglobin already has reached the optimum structure of taking oxygen? Okay, this is one question. Yeah, this is one question. Yeah.
So we have not done that, but we've looked at some allosteric proteins because we've developed, this is my great student, Jason Rocks, who did the tuning Allosterium into flow and mechanical networks. He's now a postdoc at Pankaj Mehta. But he did this really nice work where he actually asked, what can we learn about what did the network, how did, tuning these little things actually give you this new collective response of Allosterium? And so he actually developed a persistent homology analysis to understand what had been done to the network and why we got Allosterium. And he's applied that to real proteins. But we have not actually looked at this question, but about this thing about whether it's optimal tuning. The nice thing about these problems is when you have so many more learning degrees of freedom than you have constraints, okay, then there are many, many different solutions that are all optimal. There's no single optimal solution. And this is what Sid would say is below the bullshit line. I'm totally bullshitting here, okay? But the idea is that, okay, maybe it's important for biological systems to be in that limit where I have a lot more degrees of freedom than I have constraints, because then I can tune it in by evolution. I mean, right? Otherwise, it would never happen. But if you've got lots of different solutions, then the chances of hitting one are higher. Okay, so we find, for example, in our mechanical network, that if I have a mechanical network with 1,000 nodes, I can tune in several hundred allosteric sites simultaneously, successfully, no problem. Okay. But in biology, you rarely see more than 2. It's usually 1 and sometimes 2. Why? That's that's a lot lower than the maximum that you could do. But that's because you want to be successful, right? If you want it to be robust and successful and to actually get it, then it has to be in that limit where there are lots more degrees of freedom than there are constraints.
Let me go back to your mechanical network. Are you assuming your mechanical network linear in terms of the energy?
We have assumed it's linear.
Okay.
Yes. So
okay. Then my question is that when you train your network, how do you know when to stop training each step? Because if it's a non-linear network, your network may be still evolving in time.
So because it's a linear network, we can
then you have a definite time.
Then we can do
non-linear.
Yeah. But we have not tried to do nonlinear networks, but we have done it. Needy's done it in the lab, right? She has done it in the lab, and yes, it could be that if you waited longer, it would keep going.
Right.
So that's right, and that's not something that we've studied in a huge amount of detail.
Yeah, but nonlinear networks would also tend to relax more often than not, which actually might help you because of memory.
Yeah, I mean, nonlinear networks actually can be more tunable.
Yeah, it can actually help you. Okay, there's one more question here from Shipurna Sinha, Raman Research Institute in Bangalore. You have used the principle of minimum dissipation in your work. I was wondering how general its scope of applicability is.
So in physical networks, you do really want to minimize something, right? So in mechanical networks, you really do want to minimize the mechanical energy, and in flow networks or electrical networks, you really do want to minimize the power. So that's a nice property that we have in physical networks. You don't have that in the kind of biochemical signaling networks and ecological networks in these other things. So that conservation law is missing then, or that physical cost function, is sort of missing. that doesn't mean that you can't sort of still introduce a learning cost function, okay, which says I want to tune it. Yeah, I want the system to adjust itself to learn this thing. That's different from the physical cost function, but yeah, in the physical systems, you generally do have something like that.
Yeah, yeah. She's happy with your
Great
point
question.
of view. She says thanks. I assume she's happy. Any other questions? Otherwise, we'll close because it's about 12:15 now. Some people may be getting hungry.
One more
Okay.
question.
Go ahead.
Can you use your theory or method or whatever to study the protein folding problem?
Well, that's harder. So because it seems like in the protein folding problem, you don't only want it to fold to the right structure, but the whole point is you want to design the landscape to be a funneled landscape so that it naturally just wants to go to that. And so then tuning the whole landscape is a harder problem. You know.
What if you start with this? Yeah.
But maybe you know, maybe that's less important than just being able to tune it. Yeah. So we have not thought a whole lot about applying this to the protein folding problem, partly because I'm scared of it. To be totally honest. It's just such a well-established thing.
Yeah.
There's so many great people working in it.
Very busy field. Yes, yeah, that's true. All right. Let's thank Andrea for a fantastic talk today, making Saturday morning worth it.
Yes, thank you for spending your Saturday morning in this way.
great questions. Thanks for taking the time. Really enjoyed it, and have a great weekend. And best to Doug as well, because yes. I saw that he came in.
Yes, he was here. Yes.
All right.
Okay.
Bye, everybody.
Thank you so much. That was really fun.
Thank you.
Thank you.
My pleasure. Yes. Bye-bye.
Yes, those great questions.
Yeah, fantastic question. All right.
Fun.
Bye.